Now let us talk about C2. Where are the C2s? Along say 1 4, 1 4 or 3 4 or 2 4, something like that. I can take any one. I will take that 1 4 bond, right. I will take that as C2 axis. Now if I turn with respect to the 1 4 bond, what happens? Which are the rolling stones? 2 and 4 are the rolling stones, 1 and 4 are not. So 2 and 3 are the rolling stones, you are right. 2 and 3 are the rolling stones, 1 and 4 are not. So we do not bother about your 2 and 3 anymore, right, and that is not the end of the story. Do you agree with me if I say that x1 transforms exactly as x4, x2 transforms exactly as, sorry, what am I saying, I am getting carried away. y1 transforms exactly as y4, z1 transforms exactly as z4, no? x1 is parallel to x1 is parallel to x4, huh? So they are going to transform in the same way, right? First of all, they will remain in their own place, and besides they will transform in the same way also. Same with y1 and y4, same with z1 and z4. So see, of all these things, so in a 12 by 12 matrix, how many 3 by 3 blocks are there? This is a 12 by 12 matrix. See, 1 2 3 4, 1 2 3 4, there are 16 3 by 3 blocks. You cannot always multiply a number by another number and get the result. There are 16 such blocks. So we were worried because we thought that we have to work out all these 16 blocks. Now we see that we have to work out only one block. Okay, and just multiply it by 2 in this case. Alikhya, understood? Sure? Okay. Then let me draw x1, y1, z1. Which operation am I performing? C2. So what will happen to x1, y1, z1? x1 remains same, z1 becomes minus z1, y1 becomes minus y1, right? And that happens not only for 1 but also for 4, isn't it? I might as well have drawn the arrows on 4. So x remains x, y becomes minus y, z becomes minus z. Okay, so you can write the block now. What will be the block? 1 0 0, 0 minus 1, 0, 0 0 minus 1. So to make simple life even simpler, it is a diagonal block. So this is how your transformation matrix should look. You don't care about anything else because all you care about is character, right? So what is the character? Minus 2. Right, simple, very easy. A picture abhi bhi baki hai, as we will see, not right now, a little later. What is the next symmetry operation that we have to worry about? Let us say sigma h. Which are the atoms? What are the rolling stones here? No rolling stone. So you have to consider everything, but still now we are not worried anymore, because what we understand is that since they don't change places, all I have to worry about is work it out for only one atom and just multiply by 4, right? It is very simple. So tell me what will happen if I apply xy, sigma h xy, when I apply that, what will happen to x1, what will happen to y1, what will happen to z1? x1 and y1 remain the same, z1 changes sign. So if I apply this sigma, this is what I get. And the same would hold for 2 and 3 and 4. So we are going to have 4 identical blocks along the diagonal. What will be each block? Tell me now. 1 0 0, 0 1 0, 0 0 minus 1. Very good. Alright. See, now we are going so fast, isn't it? We took so much of time for C3 and now we are going very fast. What will be the character? 4. Yes, this is the, I keep forgetting this all the time. I correct it today. This is the peril of copy paste. Be extremely careful when you copy paste. That is also a lesson. There is some other mistake somewhere in some later slide also. Please point it out so that I can correct it once and for all. Alright, this is 4. Chi sigma h is 4. Now, next S3. S3 once again, it is like C3. 1, 2 and 3 change places and 4 does not. The only difference is what? Z also becomes minus Z, unlike the previous one. So, same matrix as C3, same block. The only difference is that the 3 3 element is minus 1 instead of plus 1, right. So, I can write now. What is the character? Chi S3 is minus 2. See, we have worked out everything almost. Now, Zx. What is Zx? What kind of plane is this? No, how will you write that kind of plane? What is it called? Dihedral plane, because it also bisects the angle between the C2 axes that are perpendicular to the principal axis of symmetry. हाँ? तभी तो D3 है, सही है. हाँ. All right. So apply Zx. This is Zx. Now what will happen? What are the rolling stones? 2 and 3. So we ignore them. We have to work with our old faithful 1 and 4, right? And what will happen when I apply this plane? What will happen to the coordinates x, y, z? The zx plane, right? Even without drawing, you should be able to tell what will happen. Y changes sign, the others remain the same. Very good. This. And now the animation looks a little annoying because it's too slow. We have already given you the answer. What will the block look like then? 1 0 0 0 minus 1 0 0 0 1. How many such? 2 diagonal blocks. Character? Alright, I have written it as vertical plane, I don't know why. Anyway. Even they have written it as vertical plane, so let us not get into, that is why I have done it. But it is a dihedral plane, I don't know why it is written as dihedral vertical. Anyway, forget it, does it really matter? 2. Any other symmetry operation left? No. So see, what we have then, we have this reducible representation containing the 3n coordinates of carbonate. And the representation is 12 0 minus 2 4 minus 2 2. Please take it down. 12 0 minus 2 4 minus 2 2. I show you the character table also. 12 0 minus 2 4 minus 2 2. And out of these coordinates, you know that there are 3 translational coordinates, 3 rotational coordinates, 6 vibrational coordinates. So before anything else, what we could want to do is we could want to break this down into the constituent irreducible representations. So how can we reduce this reducible representation into the constituent irreducible representations? Huh? Use that relationship. Okay, you have taken down the characters for the reducible representation, right? 12 0 minus 2 4 minus 2 2. Okay, you know this relationship. If you don't know yet, please write it down, because now you are going to work it out. Huh. 54H. This is D3H for you. Can you work out the coefficients of each irreducible representation in that reducible representation that we have constructed? What I suggest is go through Carter's book. I'll tell you which page. Carter's book shows you how to do this in a tabular manner rather than writing out separately. Okay, so that might be a little easier. This 12, 0, minus 2, 4, minus 2, 2, these are the chi-Rs, right? The character table gives you the chi-Rs. So for each of the symmetry species, you have to multiply the chi-Rs by the corresponding chi-Rs and then sum over all the symmetry operations. And when you sum over all the symmetry operations, there is some place where you can go wrong very easily. Where is that place? Do not forget to multiply by this 2, this 3, this 2, 3, etc. Because do not forget that we are summing over all R's, where R is a symmetry operation, not symmetry element. So 2C3 means there are 2C3 operations. You have to sum over all the R's. And when you do it in a tabular manner, it's very easy to see if you have gone wrong. So please read up that tabular presentation from your Carter's book. So what is A1 dashed? 1. What about the second one? A2 dashed? 0. That means there is no A2 dashed kind of vibration. What is, well, not only vibration, rotation and anything. What is E1 dashed? A1 double dash? A2 double dash? So you worked it out completely? Let me write it down and see if everybody has got the same answer. So I can write it like this. This gamma we have got. I will call this, what will I call this? What will I call this? I want to give a name to this gamma. I will name my gamma gamma 3n. Okay. So that is equal to, what is A1 dash? So I will write A1 dash plus, what is A2 dash? A2 dash 0. So I won't even bother writing anything. What is AE dash? So your answer would better be correct. 3E dash plus 2A. So nothing for A1 double dash, 2 A2 double dash. Then what about E double dash? What about E double dash? Is this E double dash or no? Or nobody has worked it out? Even if you don't tell me anything more, I can work it out. This is a one-dimensional representation. So 1. E dash is 2-dimensional, 2 into 3 is 6, 6 plus 1 is 7, 7 plus 2 is 9. How will it be 3? If it is E double dash, then it cannot be 3, right? One, 2, 3, 6, 9. So total has to be 12. But how will I make that total 12 by E double dash? Something is wrong. See, so you made a mistake. A2 dash. I will just write the A2 dash here if you do not mind. So, if that is the case, then I should get 1 E double dash. You understand what I am doing, right? The dimensionality of the reducible representation should be equal to the sum of the dimensionalities of the constituent irreducible representations, right. So, dimensionality here is 1, dimensionality of E dash is 2, and there are 3 such. So, 2 into 3 is 6, 7, 7 plus 2 plus 1 plus 1, 8, no 10, and E double dash 2, that is 12. I had better check if the answer is there. Yeah, A1 dash plus A2 dash plus 2 A2 double dash plus 3 E dash plus E double dash. So, congratulations, you are good in arithmetic. Now, what will I do? What does this gamma 3n stand for? It is a representation for what? It is for the 3n coordinates, that is all. And we know that out of these 3n coordinates, because it is a non-linear molecule, 3 have to be translational coordinates, 3 have to be rotational coordinates. So, some of these coordinates, the sum of the symmetry species that we are showing here, they are going to be because they are going to be for the translational coordinates, some will be because of rotational coordinates, and that is something that we can read off directly from the character table, isn't it? So, D3, you can see D3H, can you see? Now see, for D3H, X and Y jointly form a basis for E dashed, right, and what was your answer there earlier? 3 E dash was there. So, out of that 1 E dash goes for translation along x direction and y direction. Where is Z? Z A2 double dash. Do you have A2 double dash in that expansion? You do. There are 2 A2 double dash. So, one of them goes for translational motion Z. Okay, what about rotational motion? RZ is here, A2 dash, and Rx and Ry jointly form a basis for E double dash, right. So, what I need to do now is that I need to remove the irreducible representations corresponding to translational and rotational motion. Then whatever is left will be the symmetry species of vibrational motion. Simple? Let us do it. Did you take down what is what? Huh? Okay. No? Then do it. Symmetry species for x, y, z, Rx, Ry, Rz. So, what do I take out? So, this is gamma 3n. What I will do is I will write down what is gamma translation, or I will write x, y, z, just x, y, z. Gamma x, y, z means these will be the x, y, z components of translation, right. So, what is gamma x, y, z? Tell me. E dashed plus A2 double dash. What do I need to take out from here? I want only pure vibration, right. I have taken care of translation, now I need to take care of rotation. So, I will write gamma rot. What will gamma rot be equal to? A2 dash is that right? A2 dash plus E double dash. Okay. So, what I want to work out finally is gamma vib. Gamma vib means the representation for the normal modes of vibration, that will be equal to gamma 3n minus gamma xyz minus gamma rot. What will that be equal to? A1 dash plus 2E dash plus A2 double dashed, no A2 dash, right? A2 dash gets cancelled, no E double dash. How do I check whether my answer is right or wrong? Total dimensionality should be equal to 6. Is it 6? 1, 2 and 2 into 2. Don't forget, E dashed is a two-dimensional representation. Okay, understood? Crystal?
Total dimensionality is 6.
Is it 6 or not?
Yeah.
It should be 6, right? 3 and minus 6.
Oh.
Right? So what have we done? We have not even tried to draw the downward modes of vibration, but we know their symmetries. We don't know what they look like, but we know their symmetries. If you remember, we had said that we are going to play astrologer. We are going to work out the kundalis of molecules, and this is what we have done, right? Ram is not born yet, but Ramayana is written. So we know the symmetries of normal modes already. But is that all, or is there more? Of course, when I ask a question like that, the answer is there is more. Two things. First of all, we don't have to do all this. I can simplify this further for you. What is gamma 3n? How did we get gamma 3n? Do you remember? For gamma 3n, what you did is you took the number of atoms, right? Number of atoms that is not changed by a particular symmetry operation, and you multiplied it with the character of xyz, right? Understand what I am saying or not? So what you need to do then is that you write down this character table. Just look at the character table. Then below that, write down what is the number of atoms that do not change position upon that particular symmetry operation. So what I am saying is this. Big enough? But wrong character table. Now is it okay? Now what I am telling you is, write down another line here for n. Can you read that n? Yeah, of course you can. What is the number of atoms that do not get changed for E? 4 in our case. For C3, 1. For C2, sigma H, S3, sigma V. So now what you can do is, you can work out gamma xyz also. What did I write? Sigma H should be 0. Instead of one extreme, I have gone to another extreme, which is not good. 4 atoms remain unchanged. Hey, what are you saying? What am I asking? What is the total number of atoms that remain unchanged? 4 is correct. Shantanu, I forbid you from confusing me in future. You understand what I am saying? What is the number of atoms that don't get changed? Now see, you can work out gamma xyz. I will just write it here for the want of space. What is gamma xyz? Can you tell me? This is xy and this is z. So how do I get gamma xyz? Character for this is 3. Character for C3, what is the character for C3 for gamma xyz? For xy it is -1 and for z it is 1. So our good old friend 0. Then 0 and -1 is -1. So on and so forth, you can work out these characters for gamma xyz. Now you see, if you just keep on multiplying this n by the character of gamma xyz, don't you get gamma 3n? You understood this, what I wrote, what is n? You understood gamma xyz? Gamma xyz you don't understand? Gamma xyz is gamma x plus gamma y plus gamma z. So gamma x plus gamma y is E dash, right? And gamma z is A2 double dash. So now I am just adding the corresponding characters. Now got it? So now if I multiply each of these characters of gamma xyz by the number of atoms that remain unchanged by that particular operation, should I not get gamma 3n?